This is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see resolution of bending moment, means how to resolve that bending moment. So our lecture topic will be resolution of bending moment. So first, before that, what we have to see in thin plate theory also we have seen that some assumptions are there. So first, what are the assumptions? The primary assumptions made in determining the direct stress distribution produced by pure bending. So here pure bending is there, means there is no compression after applying, suppose this force is there. If we will apply the force like this, some compression will be there, that we have to ignore. Only we have to consider what? The bending. Okay, so means there is no compression. By pure bending is that plane cross section of the beam remains plane and normal to the longitudinal level of the beam after bending. Means whatever the plane is there on normal plane, that remains plane even after applying the bending also. So before the bending, if it is plane, then after bending also that neutral plane should remain neutral only, or without bending only. Again we see this from the line on the side of the eraser. Means from which side we will see? From the other side of that one. Just here that eraser. We also assume that the material of the beam is linearly elastic. So here again what we have to consider, that beam is elastic, linearly elastic. Means what? That it obeys Hooke's law. That's why in previous video we had also seen what? Sigma z equals to E into epsilon z. So it's a obeying Hooke's law, and that the material of the beam is homogeneous. So whatever the material is used, that is homogeneous is there. So before that one, these assumptions are required. If suppose homogeneous material is not there, means we will not get throughout the same bending moment. Wherever the material is more stronger, their bending moment will be less. Wherever it's softer, or you can say having less homogeneity, their bending moment will be more. So we will not get throughout the same bending moment. So that's why that must be homogeneous. Now, the next is direct stress distribution. So consider a length of beam that is subjected to a pure sagging bending. Sagging means what? This is, and hogging is this one. Means if anything is here, so if this is coming like this, this is called sagging. And same if this one is from this side, it's becoming like this, that is called hogging. So what we are taking? Sagging bending moment. So this is the case. Sagging bending momentum applied in a vertical plane, the beam cross section has a vertical axis of symmetry. So whatever is there along the vertical axis, it's a symmetry. So just here in this case you can see from the vertical axis it's a symmetry both the side. The bending moment causes the length of beam to bend in a manner similar to that shown in figure A. Here it is. So it will bend. So that a neutral plane exists. So here it will bend like that. So a neutral plane will exist somewhere here. It's not necessary that always neutral plane will be at the center of this one. Neutral plane will be any the plane which is not getting bent after even applying the bending moment. Before the bending moment it remains straight, and even after applying the bending moment also it is straight. And that will be the only one plane. Means what? Just above this one. So above this line, just near to here, that will experience some moment. If we are bending like, if suppose this is the, we are bending like this, then that will compressed and the lower part will get elongated or tensor. And just near to that also will experience some bending moment. But only this will not experience any moment. So that is the neutral axis. That's why it's called neutral. It's not getting bent. And also the fiber ST, this ST, that what we assume, of cross-sectional area dA, a distance y from the neutral axis plane. So from neutral axis plane at a distance, this fiber just we consider at a distance of y. Clearly before bending take place, so before bending and normal case, what happened? So just here, MP, right, just it is forming a rectangle. So MP will be equals to ST, which will be equals to IZ, that is equals to NQ. So here MP equals to IZ equals to ST equals to NQ equals to what? That is only the delta Z. This is before bending. Right. Now this is the cross section of this one. So wherever the cross section is there, here the neutral axis. What element we have considered? That as delta A. So delta A where? Along this fiber only we consider. So here this is at a distance y. So from here this is at a distance y. And what will be the maximum? That is from this neutral axis to the top is y1 and bottom part is y2. So this y1, y2. When y1 equals to y2, then that time neutral axis will pass from the middle or center. But here y1 and y2 is not equal. So that can be anywhere, that neutral. But one place definitely it will be there which is not getting bent. The bending moment M causes the length of the beam to bend about a center of curvature C as shown in figure. So now this will see here. Right now this is straight. Right now this is straight. So what happens once we will bend this one? So this will bend like this. And this will get compressed. Right. This will get compressed. So this part like this is there. So after bending, just see here. This is flat. Once applying the bend, so this is getting compressed, this distance. So just see, first this is the distance. Now after compressing, this is the distance. But this part is getting elongated. So lower will experience tension and the upper will get compressed. Same here, just see in the figure. So after applying this, now this part getting compressed and this part getting elongated. But still this I, this one, this neutral axis, that IG remains the same in size because it's not experiencing any movement. The bending moment M causes the length of the beam to bend about a center of curvature as seen here. So from this one, that at center, so from this, what? From the neutral plane at a distance R for this one, right? Similarly, from here, this is the radius of curvature of this one. Okay, so this bends at an angle of what? Delta theta. So what will be the angle of bending? This is that delta theta. Okay, so after this, once we will apply the forces, okay, so see here what happened. Like here del theta is there, so this will be Cn, because this is the last part, right? Actual, and this is. Okay, so how we can find this delta theta? Because this from here it's a radius of curvature r. So from the neutral axis we can find how much angle is forming. This one by using theta equals to L by r. So here theta is del theta, right? So for this is del theta. Okay, so from this, if suppose we are taking from here, so del theta L will be equals to what? Ig, and radius of curvature will be equals to r. So for this neutral plane we found this one. But what about this one? The same, in that case del theta will be equals to this. For the lower one, nq by this distance Cn. Because for lower we are finding. So nq by Cn. Cn will be the radius of curvature for the lower one. And for this upper one, del theta will be equals to what? For upper, Cm. So this is mp by Cn. So mp by Cm. So this will be the theta. And after finding, we can see that all the theta are giving the same values. Because why? From this same angle they are forming. The only thing, distance is different from here to here. That radius of curvature is different. And radius of curvature is different. And what is there? That arc length is also different. So this is the ratio of what? Arc length by radius of curvature. If arc length is changing, radius is also changing. So overall, the ratio will be same. If in same proportion it's changing. Same way, yeah, we are getting that delta theta value. Okay. So now, after this, what happens to just see here? In this case, you can. So this is the neutral axis. So just after drawing this here, right, this is the neutral axis which is not experiencing any moment. So the moment will be 0 at this point. So that's why here it is 0. As you will move up, it's experiencing the compression. So this just near to this axis, this is experiencing the less compression. Once you will reach here at the top, that will experiencing the more compression. Similarly, just below this neutral axis, this is experiencing less expansion or less tension. But once you reached at this point, this will experience the more tension or most tension. So just see, after applying this only, So at this point, lower compression. Move up, compression will be higher, higher, higher. At this top, the compression will be maximum. So here at this top, the compression is maximum. Come down. So while come down, here the tension will be lower, lower. Once it reaches to the last, here the tension will be maximum. So let's see here, the tension will be maximum. Right. So this is the work moment distribution. So sigma for this is Z1, this sigma Z2. Okay. So let's see once again. For that, first what we have to do, first some assumptions are there, by that only we can. So first assumption is it should be pure bending, there is no compression should be there. Okay. Then one plane is there that after applying the moment it remains unchanged before the means whatever the before applying the bending moment condition was there of that plane, that should remain the same even after applying the bending moment. Right. The next condition is what? It should be linearly elastic and obey Hooke's law, and material should be homogeneous. So these are the assumptions. Next is what? Now considering. So first here what we are taking that as sagging bending moment. So this case, and in sagging bending moment it's a symmetrical about the vertical axis. So these are the conditions for finding that one. Now also what are the bending moment causes the length of a beam to bend in a manner similar to shown in figure, so that neutral plane exists which is as yet unknown distance y1 and y2. The distance we don't know here. So from the top this is y1, and from here at a distance y to this y1 y2 we don't know. Okay. So now what we are doing, just at a distance from this neutral axis, just take an elemental strip of delta A at a distance y, and for that we can find, and then we can just integrate from upper one 0 to y1 and for this 0 to y2 in this case. But what happened before bending moment, this remains same here. So this is the cross section, that this is MP, and so it just look like rectangle. So MP, ST, IG, NQ all will be equal, which what we consider that as small element delta Z. So that is here in case of what? MIN and PGQ in this line. So these two lines are parallel, so this will be same. Okay. Now the thing after bending, what happened? So after bending, the upper layer, right, upper layer will experience compression and it will get compressed. Lower layer, it's getting elongated or experience tension. But still this neutral axis will remains same. So from this case what happened, and the radius of curvature for this neutral plane is R, along for this one it is Cn, and for this it will be either Cp or Cm, because the same radius of curvature will be there. With that we can find delta theta. So for this case, for the neutral plane, that delta theta will be equals to what? Delta L by radius of curvature. So delta L by R. So L is equals to what? Ig. So Ig by R. For this lower surface, it will be delta theta equals to NQ by Cn. For this upper, it will be C, that is MP by Cn. That will be delta theta, and delta theta for all the cases it will be shown, it will be same, because the radius and arc length is changing in the same proportion. Okay. Now according to that only we can say that how the shear stress distribution will be there or bending moment. So as we can see from the neutral axis it's a 0. So at neutral axis it's a 0. Moving up means it's experiencing what? Compression. So but lesser compression. So this part lesser compression, lesser, higher increase, and here it will be the maximum. So here again less, increasing, and here it becomes maximum. Now come down. So just below this one experiencing lesser tension. As we move up, go down, it will be here will be the maximum tension. So here at this point it will be the maximum tension. So this is the shear stress distribution, right? So that is here direct stress distribution. How this direct stress will be there. Okay, so if you have any doubt, you can just comment on the video, or you just contact me so that I can clarify your doubt. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.